He is now principal engineer and business center business leader, industrial water at Stantex, water business headquartered out of Houston, Texas. Over 19 years, he has led industrial water programs and worked on implementation of membrane-based systems across energy, oil and gas, power, advanced manufacturing, and mission-critical sectors, including data centers, combining technical design, project management, and stakeholder engagement. His portfolio covers process technologies, including membrane filtration and industrial reuse strategies. He has authored and presented work on water sourcing and circularity for large energy and infrastructure projects. He's got a long bio. In Texas, Shilhan and his team have supported dozens of proposed data center facilities, working with owners, utilities, and regional managers to align cooling demand with sustainable water supplies. He's especially enthusiastic about the opportunity to use produced water as a resilient source for data center cooling in West Texas. What treatment trains are required, how quality targets map to cooling technologies, and where policy mechanisms, such as Texas's industrial reuse framework, enable fit-for-purpose infrastructure development. He also outlines practical permitting and partnership models that can de-risk schedules while delivering community infrastructure benefits. I also mentioned he's sponsoring tonight's dinner, so. So without further delay.
I'm really excited to be talking to this group today because it kind of brings together two industries that one that I've been very involved with over the past more than a decade, the oil and gas industry, and a new industry that's kind of entering the fold as a potential off-taker in data centers. So seeing these kind of behemoth sectors in the market kind of come together and do development is really interesting, and trying to solve their problems, especially around water, is something that I've been passionate about. Finally get the opportunity to see potentially things happening. So I work at Santec. We always start with the safety moment, kind of look at risks and safety in the context of energy. If there's some energy source out there, there's probably some sort of a risk. So that's just a pretty good way to kind of take a easy look at, okay, there's something high up, there's potential energy, it can fall on me, something hot, that can cause bodily harm. So I think this is a pretty interesting tool, something pretty useful, and wanted to share that with this group. In terms of the agenda, I think the last couple speakers really spoke a lot about the things that I'm, going to touch on briefly. So they got into it in depth, which I'm really grateful for because I'm no cooling expert. But really what I want to talk to you about is the potential for really increasing our water supply. Like, what we're talking about in a lot of these cases is where do we get it? Groundwater, surface water, wastewater reuse. But really what we need to talk about is how do we get more water? And there's really not that many options. And this is a case where water is a problem for one industry, but could be a solution for another. So I'm going to talk a bit about produced water, what it is, kind of the challenges around it, what is typically done and what could be done. I'm going to talk a bit about data centers, not as in depth as Luis, but just, the water demands and some heuristics that we have around if you're going with a water heavy kind of portfolio for your cooling, what you could look at for volumes, things like that. Some of the risks and barriers, and then, conclude with some final thoughts. Hopefully I didn't put in too many slides and we have some good Q&A afterwards. So in the Permian Basin, we actually produce more water than we produce oil. Actually, one of my close friends who works for a major said, the oil and gas industry is the only water positive industry, which it took me a while to get around to that, but yeah, it's true. In the Permian Basin, currently about 900 million gallons of water is produced on a daily basis. About 300 million of that is reused for hydraulic fracturing and continuing production, so for upstream oil and gas uses, but 600 of that 900 goes downhole. And that's projected to grow over the next decade. And for my oil and gas clients and people I talk to, they say they want to be producing the Permian for at least the next 30 years. So the water cut is just going to keep growing. This is just going to keep becoming a bigger problem. And of course, they're going to want more oil and gas out of that region. But what's been the traditional way of water management is coming to a bit of a halt. And that's simply because if you think of the subsurface as a big tank, that tank is running out of space. We've seen this with deep well injection, which has been the traditional way of disposing of produced water, getting seismic events because of just the lack of pore space in the deep subsurface. They've transitioned over to shallow zones, and there's a lot of orphan wells that aren't plugged correctly, and we're seeing well blowouts because of the pressures within the shallow zone. And so just in a nutshell, it's becoming harder. And this is a problem that what I've heard between 2030 to 2032, we're going to be running into some serious problems. And just to make it clear, this is an existential problem for the oil industry in West Texas. Can't manage or produce water, you can't produce oil. All right. So the deep well injection challenge, earthquakes are triggered. I've pulled some public information around the earthquakes, and you can just see that they're last year's presentation, I had two snapshots a decade aside by each other, but they're growing not only in frequency, but also in the scale of these earthquakes. And like I mentioned, it's just because of a lack of space. And what happens is when an earthquake happens, the Railroad Commission creates a zone around which those wells need to be shut off for some amount of time until the pressures go down. That actually adds cost to the producers, because if you have less supply of injection capacity, your cost goes up. And then on the shallow well side, what you're seeing is these orphan wells are becoming pressurized, and they can't hold the pressure. And you see these big blowouts on the news, and it's it's sad, because it's really, like, if you look at this photo, I don't know. Yes, if you look at this photo, that's a bulldozer right there. So these are massive. They continue for some time. And so obviously this is a community issue in West Texas, and they're getting a lot of pressure to manage this in the proper way. So what are the options? What do you do? You can move the water away to some other places where injection has not been done, but this is very expensive. There's a new pipeline that's been announced that's going to cost nearly $500,000. And it's really not a long-term solution. It's kind of kicking the can down the road. These volumes are massive. And then also you can treat to reduce the volume, because you won't be able to eliminate it. You can reduce the volume, and that's been something that's been looked into, but it's been very costly. But as technology has advanced in this space, I think that the costs are becoming somewhat reasonable. So, there are options, but none of them are free. And really, that's what the oil industry needs to kind of come to grips with. And that's where we're at today. In terms of produced water, there's no standard produced water spec. It's going to be different from the same well on a minute by minute basis, or even more regularly than that. it's gonna differ between like a couple miles down the road, it will be very different. In the worst case scenario, we've seen salinities up to 170,000 milligrams per liter of TDS. And that ranges all the way down to 100,000. So it's it's still very saline. The salinity of seawater is around 30,000, so 3 times that at the very minimum. And it's complex. It's got all sorts of cats and dogs in it. Oils, different scaling components, metals, radionuclides, you name it, it's in there. And it's also got production chemicals, trace chemicals that are coming back from the production that was put in there to begin with. So all that to say, it's a very challenging water to treat, and and being a chemical engineer, you can treat anything, it's about cost, right? So it's very costly. I'm gonna flip over now to the data center story. I think Luis covered a lot of this very well in his presentation, but really just what do data centers need in order to exist? They need a land mat or a place to put the facility. They need power. They need fiber. They need a skilled workforce, and of course, they need water. And so, the Permian Basin is unique in the sense that it's got lots of gas, and the ability to do behind the meter power is very appealing because of the queues to get into the grid. And so it's got a lot of gas that you can do behind the meter power. It's got a lot of land. There's major highways through there, so it's got fiber. It lacks water, in the sense of the sources that Luis listed, right? And so, but it's got a lot of produced water. And so trying to tie these two together is a really interesting thing. And I apologize, I noticed after I sent my last version to Gary that there was a little bit of an error here. So I'll just talk through this. High level, again, Luis covered it. You can have very heavy water cooled systems, and you can have air cooled systems, and you can have many things in between. For the purposes of this set of slides, I'm going to be more focused on the water cooled systems because, like Luis's slide said, it's the most energy efficient. So if you can have a better, forget the term, energy ratio, energy efficiency ratio, power, PUE.
Power, PUE.
PUE. If you can have a better PUE, that's ultimately the best. So if you have water, you use it. But even with the hybrid systems, the ones that are not purely air or water, there's going to be some water demand. And sometimes in West Texas, even a minimal amount of water demand is not something you can fulfill from looking at your traditional sources. And in terms of the water quality specs, I wanted to paste in the produced water quality specs in here, but I would have gotten too busy. I'm gonna ask you all to jog your memory about how bad it was. This is very clean. And the volumes, if you were to use like an evaporative cooler or a swamp cooler, you could be looking at 10 million gallons per day per gigawatt, roughly in West Texas. And assuming 5 cycles of concentration, this is the water quality you'd want to get to. So from, your 150,000 milligrams per liter TDS to 550. That's the gap, right? So how do you treat produced water? You got to really go step by step to make sure you're getting out all the different things that could harm the desalination technologies down the line. Typically what happens is produced water is co-located to a facility that would do some very coarse separations through what's called a gun barrel and some walnut shell filters, really to get your oils out now you got mostly water, and to start getting some of the soluble oils out. Through the course of that, you may have some precipitation. And then what you do is you go through a pretty extensive pretreatment train. If you were going to do desalination, you would look at what the technology is, and we've done a lot of work more recently around membrane-based technologies that are kind of advancing. And so if I was talking, and I do have a block flow diagram around membrane-based technologies, but you do the pre-treatment required, you do the desalination, you do some post-treatment. And in this case, it was looking more at the surface water discharge types of things. So for industrial use, maybe not all of these apply. This is that block flow diagram I was talking about. I think that this is something quite interesting because, like I said, the challenge around produced water treatment is really the cost, right? And I can put some rough numbers to this. Like if you were looking at a thermal-based solution, you're looking around $3 per barrel fed into a system. Per barrel of water fed into a system. And in comparison, an injection well costs about 70 cents. And so that's a big gap because the thing to consider is you get 4 to 5 barrels of water per barrel of oil. So if you're going to mark up your barrel of oil based on your disposal costs, you're actually looking at $15 as opposed to 3, right? And so trying to minimize that cost of treatment is really where a lot of focus is right now. Membrane-based solutions offer some promise on paper, and more recently in the field as well. Some proof has been done, and they're kind of coming up on that TRL level. But it does require significant pretreatment. So, you know, we talked about this stuff done in the produced water collection area, and then this would be the pretreatment potentially around membrane-based solutions. You may do some softening, you may not. You'd have ultrafiltration, you'd probably have some sort of final polishing for your dissolved organics prior to going into your reverse osmosis. I think the technical term now is LSRO, low salt rejection reverse osmosis. The branding around OERO and this has been a little bit confusing. So, but nonetheless, and then you go into your post-treatment trains. Brine management still is an issue, right? And you still end up with 40 to 65% of what you sent in as brine. And so that's, you know, something on the order of 150 to 250 million gallons a day still that would need to be injected. But it's a significant reduction in the volume. And you know, my friends who are geologists say that that would make a big difference. So that's kind of the holy grail that we're trying to get to right now. And as I mentioned earlier, the cost of treatment and the impacts on the economics, I think it's really important to think about this from the big picture. The price of oil really permeates throughout, right? Like when the prices of energy go up, the groceries get more expensive. Like there's so many different things that it touches that even a small, like when I thought about this earlier in my career, I used to think like, what's the big deal about some small dollars on a barrel? But you gotta think about this in the big picture and also think about it in the context of the oil producer who's actually selling the oil and the water as a waste product. And so, like I mentioned earlier, multiply out the number of barrels of water to what that is equivalent to the barrels of oil, and that's your actual cost of the the waste management. This actually does not take into account the fact that you still need to inject that 60% or whatever. So that's something that I thought of later on after I put this stuff together. But so in essence, you're looking at somewhere between a 5 to 10% increase. I just took the price of gasoline now and tried to come up with this. But that, you can kind of see the inflationary impacts that would have on everyday life, right? Um, there's a lot of risks. I think the main thing is that this needs to be done at scale pretty fast, and it hasn't been done yet. And when you're talking about putting steel in the ground in the next 5 to 7 years, um, to do a new process at this scale, I think that's just something that, everyone's gonna have to kind of come to terms with, figure out how to, manage that risk. But the technical risks are that the treatment technologies, especially the ones that are at lower cost, and there's certain ones that are coming up that are promising, but not quite there on the TRL scale. These aren't mature. It would be first of its kind at scale. The water midstream infrastructure is not built out. So, considering how much water is produced, it's not really transported and collected anywhere in order to treat at scale. It's transported enough to be able to inject in different locations. And so that is a big opportunity, or it's a risk to the schedule that these producers are meeting, but it's an opportunity for many companies who are looking to participate in this new economic leg of the oil and gas industry. Operationally, oil and data center companies aren't water management companies. And just like in our day-to-day life, kind of working with these two entities, like they're speaking past each other. One is speaking in barrels per day, one is speaking in gallons per day. And it's just there's so much that's already disconnected, and neither of them really know how to manage water. I think it's a big opportunity for, again, that midstream water type of company to be able to go in and provide that expertise. And so that's we have clients who are like that, who are looking to provide that service. So that's something that will be coming up. And then regulatorily, they don't really know how to provide the right rules around this. One of the reasons that, I chose to talk about produced water for data centers is because for an industrial off-taker, that regulatory risk is much lower. And evaporation ponds and things are already established. So there is a sense that the regulators won't have an issue with this, but it's still a risk because no one's really put some guidelines in place. And the framework is still in the works. There's definitely commercial risk, and related to the opportunities, like I think all these risks are really, if you look at it on the other side of the coin, there's a lot of opportunities here. I think the main thing is, if you think about the price of water management going up, that allows for innovation and people to work in the space. And so, just like when the price of oil is high, that's when there's investments made, right? And so, yeah, personally, I feel like there's a lot of opportunities. I did fail to mention, this is a little bit of a unique space for chemical engineers working in water. I've been working in the space for 20 years now, and I think that as we go more into industrial reuse, that Luis brought up, really, it's a place where chemical engineers fit well, knowing the types of chemical contaminants that are generated through industry and the ways to process that. So with that, conclusions. So regardless of how produced water management changes, the change is inevitable and it's imperative. Treatment for volume reduction is a viable option based on our analysis. Like I mentioned earlier, water supply is not unlimited. And looking at ways to increase your water supply through seawater desalination or produce water reuse, those are, I think, actually things that can change the game as opposed to robbing Peter to pay Paul, right? And so, technology exists, but the cost is the main barrier. Regulatory framework for discharge and use for beneficial crops is still a challenge. I think that's another area that they're looking at, beneficial reuse as a pretty low hanging fruit. Data center offtake offers a win-win. Produced water is a problem. Data centers need water. I think that the cost challenge can really be addressed there with some cost sharing. If the data center clients are comfortable with paying more for their water, but being in the Permian Basin. So that's definitely a win-win on that one big issue. And just like to highlight that, with air-cooled options, the power demand goes up, and the water demand goes up. So I think the water demand doesn't go up as much as it would if you were just going with evaporative coolers on a data center, but there's still water demand from your power. So just something to think about, thinking about it from a whole system perspective. And that is the end of my presentation.